Hello everyone! Today I would like to share with you a story about the biggest hot topic in the NLP world, at least at the moment of creating those slides, because the situation is quite dynamic. It's finally time to familiarize with the GPT family, including ChatGPT. But as always, let's start with the outline of our meeting. First, we will connect the dots between the idea of the transformer architecture and GPT models, which will lead us to a formulation of the definition of GPT. This will be very related not only to transformer, but also to one of the other approaches already discussed. In the subsequent part, we are going to discuss the next iterations of the GPT models, and then introduce a branch of GPT models focused on following instructions or interacting with humans. This part will cover InstructGPT and ChatGPT. Finally, we will discuss the current situation in the context of the influence of those models on humankind. So, without further ado, let's start. The transformer architecture presented in the paper entitled "Attention is All You Need" in 2017 was a breakthrough in the NLP world. It was an encoder-decoder network that showed us that we can process sequences much more efficiently using the attention mechanism only, getting rid of recurrent connections that were widely used previously. This change allowed us to train models much quicker as compared to recurrent neural networks, where we had to process tokens in a sequence. We had to read the previous token to process the next one. And in the transformer, each network layer might process all tokens at once. As it is an encoder-decoder architecture, we can extract and interpret both of these ingredients. Encoder here is used to transform tokens into embeddings, vector representations conveying the meaning of words, and the decoder uses those generated embeddings to produce a sequence of outputs. An example of a problem requiring both an encoder and decoder is machine translation, in which, for example, when trying to translate English text to Polish, we first encode the English text as vectors processable by computers and then use those vectors to generate a sequence of tokens in Polish. And this task, producing a sequence of tokens, is handled by the decoder part. Both encoder and decoder can be used to create language models. In the lecture covering the bird family, we learned that we can train the transformer's encoder with a classification head on top of it, which tries to predict which words are masked. Similarly, the decoder part predicts the next token based on the previous sequence we have. For instance, in the machine translation task, based on the knowledge about the input sequence, such as the sentence Marysia ma małą owieczkę, the decoder produces the output sequence token after token, trying to predict which token is the most likely one as the continuation of the existing sequence. The model which predicts the next token based on the previous ones is called an autoregressive or causal language model, while the model that tries to predict the masked token is called denoising autoencoder. Both of those approaches, predicting a masked word or predicting the next word, require the model to understand the language. We need both domain knowledge and grammar-related knowledge to decide which word fits best at a given position, and both of these could be extremely useful when used to solve various specific tasks, like we already learned in the context of the BERT models. Today's story will be the story of the transformer's decoder and the language model that is a causal or autoregressive one. In other words, predicting the next token in a given sequence. And this will be the story of the GPT model. Indeed, the GPT model is the decoder part of a transformer, and this decoder is pre-trained with the autoregressive language model objective. This implies only a small modification. We need to get rid of the multi-head attention between encoder and decoder, as there is no encoder here. The GPT abbreviation stands for Generative Pre-training and was introduced in 2018 by Alec Radford and others from OpenAI in a paper entitled Improving Language Understanding by Generative Pre-training. This paper is not available on archive.org, but you can find it easily online. I've put a link to it at the bottom of the screen. The papers related to GPT are really easy to follow, so I encourage you to take a look at them. The idea behind the paper is very simple. Let's use the transformers decoder to perform two steps. First, given some large textual corpus, pre-train a language model in an unsupervised way, and then fine-tune that language model on a supervised task. And this approach was found extremely efficient. Formally, the objective of the pre-training step is to maximize the likelihood presented in the slide. The U elements represent tokens in a corpus, and K represents the context window. We can interpret it as, based on the K last tokens, learned a model that will be able to choose the most probable continuation. To achieve this, we simply transform our input sequences into one-hot encoding vectors, then multiply each one-hot encoding vector related to a given word by a static word embedding matrix, so that the static word embedding is selected for each token, and subsequently we add positional embeddings, the area of which we already discussed in the context of the transformer. Then we pass those representations through a transformer's decoder layers, and finally we apply a softmax function which allows us to predict the next token in a given sequence. Then, having a model taught on a large corpus to predict the next token, we move to the fine-tuning phase. In a fine-tuning phase, we have a labeled dataset C, where each input example has some label assigned. For example, we may have email documents labeled with the information on whether a given document represents spam or not. Our goal here is to predict the label based on the content of the example, so that here we maximize the likelihood of assigning a correct label Y. To make it possible, the representation produced by the top decoder block for the last token in the sequence is multiplied by another weight matrix, which, when softmaxed, produces the probability distribution over classes. So this special matrix learns to transform the final embedding related to the last token to a decision, to the labels that we know. However, the authors found out that it might be reasonable to add yet another auxiliary objective in the fine-tuning phase. We not only learn to predict the label, but we continue the training of our language model by fine-tuning the language model on that supervised data. Those two objectives are then weighted and summed. We introduce a special value lambda, which determines the importance of the auxiliary language model fine-tuning phase. To sum up, the training procedure involves two stages. First, the language model is pre-trained on a large general domain corpus, and then it is fine-tuned on a labeled, a supervised dataset using two weighted objectives: the language model objective and the classification objective, where our goals are to learn better representations of words in a given domain and be able to assign correct labels. And this scenario might remind you of something. In the lecture on contextual embeddings, we introduced ULMFiT, which provided some guidelines on how we can utilize transfer learning from language model to a classifier. And this is almost the same thing. Both here and in ULMFiT, we had an unsupervised language model pre-training, and then in both ULMFiT and GPT, we have a language model fine-tuning on a supervised corpus, as well as a classifier training. The biggest difference between these is the use of the transformers decoder in the GPT model and the recurrent neural network in ULMFiT, while the high-level idea is more or less the same. Because we come back to the transformers decoder in this lecture, let's provide a short summary of how it works. If you would like to get all low-level details, these were described in our lecture on transformer. Some of the next slides will reuse visualizations that come from an excellent tutorial on GPT models provided by JLMR. You can find the link to that tutorial at the bottom of those slides. While it focuses on GPT version 2, the most of the implementation details are the same for GPT version 1. A transformer's decoder consists of a stack of decoder blocks. At each step of a given sequence, it tries to predict the next probable token based on the previous ones, until, for example, a special end-of-sequence token is produced, or a given number of tokens is generated. As we can see in this picture, a likely continuation of the text, as in the angle brackets representing the beginning of a sequence, followed by words robot must obey, is the word orders. The generated word orders is then put at the end of the input sequence, and the generation procedure is repeated. To achieve it, the model uses a stack of decoder blocks, each of which consisting of a multi-head attention layer and a feed-forward layer on top of it. There are also residual connections and layer normalizations, which are not presented in this visualization coming from the blog of JLMR, but are shown in the original transformers decoder as add and norm blocks. These layers, as described in the lecture on transformer, have an auxiliary role. They help train deep networks, and they improve the training process by normalizing layer outputs. Each multi-head self-attention layer stored in a decoder block is composed of a selected number of attention heads. The goal of an attention head is to determine the relevance of already seen words to the current one. As we can see in this slide, when trying to predict the next word after it in the context of an input sequence, a robot must obey the orders given it. The self-attention mechanism calculates how relevant each of the words in the sequence is to understand the word it. The highest importance here is related to the phrase a robot, because it is the thing that it refers to. The multiple heads allows to introduce multiple dimensions of relevance. Some heads will focus on semantics, some others on syntactics. For example, whether a given thing behind it is a masculine or feminine noun. This might impact the form of subsequent words in some languages. This mechanism was described in detail in our lecture on transform. At each step, a given token is transformed to a new representation that is aware of the context and which allows us to predict the next token. Then we simply add the generated token to the context as the next input, and we repeat this procedure. So in this slide we see the context as in the angle bracket followed by robot must obey, and having produced the word orders as the continuation, we add it to the context, so the next input in the subsequent step will be, as in the angle brackets, robot must obey orders, and we continue the process of generating the next tokens. However, there are some important details we have to mention now. First, as in the original transformer, the attention mechanism requires us to compare each pair of tokens to calculate so-called attention matrix. We are going to introduce many attention matrices because we have multiple decoder blocks with multiple attention heads. Moreover, if we use large batches of data while training the model, these attention matrices might become heavy. We will have multiple of them. For this reason, the authors of the transformer architecture decided that the context size considered should be not longer than 512 tokens, making the size of the attention matrix not bigger than 512 square. The authors of GPT utilized the same limitation. Here, GPT considers only last 512 tokens while processing them through decoder. However, realistically, 512 tokens is not that bad. Many documents might be shorter than that, and in many situations, remembering only the last 512 tokens to predict the next one will be enough. But it strongly depends on the problem we have and the dataset we process. The second detail we have to mention here is the idea of masked attention. We already discussed it in the lecture of Transformer, but it is so important here that we will summarize it shortly. Assume that we are training our language model. In that case, we can process a given sequence by a decoder and predict which word should follow a given one for each position in the sequence at once. We know the original sequence, so during training, it is possible to introduce such a parallelization. However, during training, we see the whole sequence, and this might be a problem. When trying to predict the next token after must, we must pretend that the subsequent tokens obey orders end of sequence are not known to us. And to do that, we need to introduce masked attention. For each time step in our sequence, we might create a separate row and visualize it as presented in the slide. The author of the blog post from which the image comes from decided to omit the first begin of sequence token and start with the word robot. Each row here visualizes a different time step. At the first time step, based on the first token, we want to predict the second one. Then, in the subsequent row, based on the robot must, we want to predict the next one, obey. We can see that in order to predict the next word, we must focus only on the subset of the sequence. When trying to predict the second token, we pretend that we don't know the continuation, so that it is marked in gray in this picture. In the second step, we know two words, and we gray out each token after the second one. How to force the network to omit the continuation to prevent cheating? When calculating the attention matrix, we multiply the keys matrix and query matrix, the result of which is an attention matrix, which produces so-called attention scores. Each row in the matrix represents a given token, and each column in that row represents how important is the token related to that column to understand the word related to that row. This is the matrix we referred to earlier in this lecture, telling that the dimensionality of it in GPT-1 was set to 512 tokens at most. The procedure that we use to prevent cheating is exactly the same as in the original transformer. We create a mask matrix of the same shape as the attention matrix and fill every value above diagonal to minus infinity. Then we sum those two matrices, attention matrix and mask matrix. As a result, we obtained a masked attention matrix, in which every value above the diagonal will be equal to minus infinity. Applying the softmax function over the rows, we obtain the expected behavior. The softmax cells containing minus infinity values will be transformed to 0. As a consequence, the network won't have access to those future tokens. It won't be able to see what embeddings are related to those future tokens. Each row of this matrix representing masked scores represents a given time step. At a given time step, the values in the row tell us how important each token is from the perspective of the current time step. When processing the first word robot, the network can only access the first token, so that the whole focus of the network is put on that single token. As we can see, after softmax, the attention score in the first row is set to 1 for that first position related to the word robot, and other words are zeroed. Please remember that rows and columns here represent tokens in our input sequence, so that the first column represents the word robot, the second one represents masts, etc. Then, in the second time step, in the second row, trying to predict the continuation of the words robot must, we see that the word must is slightly more important than robot. We see that in that attention matrix. However, we prevent the network from seeing the next words, especially the word obey, which we try to predict. So we don't cheat here. Applying softmax zeros the values related to the positions of those future words. And this is it. The mechanism of masking is used to be able to process the whole sequence at once, predicting the continuation for each time step in parallel. By adding a matrix with values above the diagonal set to -infinity, we zero the attention scores related to future tokens. The masking procedure is useful while performing the training, as in the inference mode, having a model that is already trained, we don't have any future tokens. Then the decoder produces tokens sequentially, token after token. We don't know what the future will be because we are creating it. You may wonder, what if the network makes a mistake here? What if it predicts a wrong token as a continuation? For example, what if the continuation of the word robot, according to our network, is the word place? The answer is, the outputs don't affect subsequent steps in the training phase. Even if the network makes a mistake here, we use a solution called teacher forcing to put the expected word as the next input instead. As we can see in the slide, at each time step of a trained model, if we make a prediction, the prediction is put as the next input of our network. However, during training, we may use a slight modification of that process. If during training we make a mistake, as presented in the second visualization, predicting the unexpected word place, we might simply ignore the output of the model, and in the subsequent step, we substitute that output with the expected word. We know the whole input sequence, so we don't need to use predictions to add next tokens. This way, we prevent the continuation to diverge over time from the expected sequence. And this is something that allows us to process the whole sequence at once. To finish the summary of the transformers decoder used in GPT, we will mention the input representation. Here, each input token is represented as one-hot encoding, so that the whole sequence of tokens represents a matrix U, consisting of those one-hot encodings related to subsequent tokens. This matrix is then multiplied by a matrix WE, which is visualized as the token embedding matrix WTE in this visualization. As a consequence, we obtain a matrix where for each of the input tokens, we have a static embedding representing a given token. Finally, we add a matrix with positional embeddings in the equation represented as WP, which is visualized as the positional embedding matrix WPE in this visualization. These are then processed by decoder blocks. The positional embeddings are not based on sine and cosine functions, as in the original transformer, but are learned ones. The network learns the weights in that matrix along with other parameters. Moreover, because the context size is limited to 512 tokens, the number of rows used here is equal to 512, as the network can't process longer sequences. The input sequences are processed using the BPE algorithm to tokenize our inputs. We introduce 40,000 merges. This makes the vocabulary size of the GPT model to be slightly bigger than 40,000 elements, because we also add single characters as the initial vocabulary, and then we introduce all that merges. And each of the input token representations consists of a one-hot encoding of the dimensionality of our vocabulary. And this is the idea behind GPT. We learned that in order to make a model able to predict the next word in a given sequence, we use the same decoder idea as in the original transformer, with only few modifications. Some of those modifications we already discussed. These are the lack of the encoder-decoder multi-head attention module due to the lack of the encoder, and the positional embedding matrix that is learned here instead of using sines and cosines. Additional differences refer to the size of the model. Instead of using 6 decoder blocks as in the original transformer, we have 12 of them. We have a hidden state size, the embedding size, equal to 768, a value that is exactly between the transformer base, which used 512 values, and transformer big, which used 1024 values. Similarly, we have 12 attention heads, with the original transformer base utilizing 8 of them, and the big one utilizing 16 of them. The size of the feed-forward network is set to 3072, which is also between transformer base and big. Transformer base used 2048 and transformer big 4096. These modeling decisions make the model comparable in size to bird base, which contains the same number of attention heads, the same embedding size, and the same number of blocks. So in the consequence, the size of the model is very similar. Bird base consists of 110 million parameters, while GPT-1 consists of 117 million parameters. In order to adapt the model which predicts the next token to the classification objective, the inputs of the tasks are pre-processed appropriately depending on a given task. For each task, we wrap our text with special begin of sequence and end of sequence tokens. The first one is in line with the training step, which predicts the first token after the initial signal. The end of sequence token represents the input, and the embedding assigned to it is used to classify the whole sequence. In the context of classification, the story is simple. We read the text and use the final embedding to classify it to generate a given label. For tasks in which we have pairs of inputs, like textual entailment, we were having a premise and a hypothesis. We want to decide whether there is an entailment, contradiction, or neutral relation between these. We introduce an additional delimiter marking the end of the first input. Here we use the $sign. Then, similarly, the final embedding after reading the input is used to perform classification. Considering the textual similarity, the authors decided that because there is no preference here on the order of inputs, the two possible orders will be processed independently, and then the final embeddings will be summed and classified. And finally, if we have, for example, question answering systems with multiple choices to select from, we can process a question with each possible answer independently and create embeddings related to those answers. In the example on this slide, we can produce 3 vectors that, if processed through some binary classifier, deciding whether a given answer is a correct answer or not, allow us to select appropriate ones. If the embeddings are passed through a linear layer with the sigmoid activation, for each answer we obtain a probability of a given answer being the answer to the question, so we can create a threshold above which we interpret all answers as correct ones. As we can see, this way of processing allows us to cover a variety of natural language processing tasks. At this point, we know how GPT works. It predicts the next words based on the embeddings calculated in the decoder. We also know how it is used in the training process. We covered the idea of causal autoregressive language model, and in this slide we showed how we can utilize such language model to classify things. We simply add new classification heads, new matrices of parameters that assign labels to our texts. We simply extract the last embedding and multiply it with a matrix and apply a softmax activation function to classify our document. Now it's time to discuss the datasets used to train the original GPT model. The first GPT model was pre-trained in an unsupervised way on the books corpus dataset. This included over 7,000 books, and the choice of it was motivated by the fact that books might contain many fragments in which modeling long-range dependencies might be crucial to understand the text and being able to predict the next tokens. For supervised fine-tuning, they decided to select various NLP tasks, many of which we can find in the glue benchmark. As we already saw in the previous slide, these cover classification, natural language inference, question answering, and semantic similarity between texts. GPT trained on such datasets, first pre-trained on books corpus and then fine-tuned on those tasks, led to great results. In the context of natural language inference tasks, the authors collected 6 datasets related to natural language inference, or NLE for short, and compared GPT with top-performing models. In 5 out of 6 cases, GPT produced the best results, beating even those methods that were based not on single classifiers, but whole committees. Those 5x and 3x markers represent numbers of models included in a given committee. In Citail and QNLE, GPT beat the competitors by a large margin. 5 percentage points increase on accuracy in Citail and almost 6 percentage points in QNLE. Similarly, at the moment of publication, it outperformed other models on several question answering tasks. In all 4 cases, the model produced the best results, and the difference between previous state-of-the-art and the new state-of-the-art generated by GPT is even bigger. In the story close task, the evaluation metric value was almost 9 percentage points bigger. Also, on other tasks, the quality of GPT was very good. The authors not only compared their solutions to state-of-the-art models, but they also dive deeper into the analysis. First, they checked whether all decoder layers are useful. They verified how the results will change depending on the number of decoder layers from a pre-trained model transferred to a supervised stage. As you can see, the more layers we used, the better the results, with the highest quality of solutions obtained while reusing all layers from the pre-training stage. As we can see, all layers are useful. They also compared LSTM models with GPT models in terms of the quality of solutions for so-called zero-shot tasks. In a zero-shot task, we don't fine-tune a given model on a given dataset, but we try to use that model and check whether it can produce answers out of the box without being fine-tuned on the dataset. The details on the evaluation procedure are described in the paper, the link to which you have at the bottom of the slide. The authors compared models on several tasks and drew a chart using a different color for different tasks. They also used the same color but different kinds of lines to make the comparison between LSTM and GPT easier. The solid lines represent GPT, while the dashed ones LSTMs. As we can see, at least 2 conclusions can be drawn from that figure. First, the transformer-based models outperform LSTMs on each task. The possibilities given by the multi-head self-attention mechanism are much larger than those of LSTMs. Second, in the context of LSTMs, we see some major drops of the quality as the number of pre-training updates increases. These are not that visible in that context of GPT, so that GPT has less variance as it learns. A detailed comparison of GPT and LSTM networks, consisting of one LSTM layer with the hidden state equal to 2048, showed that the scores of the full GPT model is better on 7 out of 8 tasks listed. Only in the context of the MRPC task, which stands for Microsoft Research Paraphrase Corpus, which is used to test models' abilities to measure textual similarity, the LSTM model beats the full GPT model. In some cases, the difference is huge. For example, in the context of COLA, in which we have to decide whether a given sentence is grammatical or not, the transformer scores about 15 percentage points higher than the best LSTM. As the authors also performed appellation studies in which they evaluated the quality of the model without unsupervised pre-training or without auxiliary language model fine-tuning on a supervised corpus, we also see that fine-tuning a language model on supervised tasks helps obtain better results using GPT for tasks with large datasets. Moreover, unsupervised pre-training is really helpful. No pre-training leads to a drop of performance about 50 percentage points in the context of GPT. As we can see, the idea of using the transformers decoder, pre-training it on a causal language model, and fine-tuning on a downstream task led to great results. So this branch of research was continued by OpenAI in next years. A year after GPT version 1 was published, a new model called GPT-2, GPT version 2, was released. The summary of GPT-2 model is best introduced in the abstract of the paper introducing it. The paper is entitled Language Models are Unsupervised Multitask Learners, and the paper is written by Alec Radford and others from OpenAI. It was published in 2019. In this slide you can find an excerpt from the abstract of that paper. Natural language processing tasks, such as question answering, machine translation, reading comprehension, and summarization, are typically approached with supervised learning on task-specific datasets. We demonstrate that the language models begin to learn these tasks without any explicit supervision when trained on a new dataset of millions of web pages called web text. When conditioned on a document plus questions, the answers generated by the language model reach 55 F1 score on the COCA dataset, matching or exceeding the performance of 3 out of 4 baseline systems without using the 127,000 training examples. The capacity of the language model is essential to the success of zero-shot task transfer, and increasing it improves the performance in a log-linear fashion across tasks. Our largest model, GPT-2, is a 1.5 billion parameter transformer that achieves state-of-the-art results on 7 out of 8 tested language modeling datasets in a zero-shot setting, but still underfits web text. Samples from the model reflect these improvements and contain coherent paragraphs of text. These findings suggest a promising path towards building language processing systems which learn to perform tasks from their naturally occurring demonstrations. In this abstract, we find 3 extremely important pieces of information. First, training an autoregressive language model, a causal language model, like GPT, allows us to solve tasks in a zero-shot manner. And the results achieved on question answering tasks are better than some baselines even without training on that task. However, there is a cost here. GPT-2 contains 1.5 billion parameters. That's huge. There aren't many differences between GPT-1 and GPT-2, and we list it here in the slide. Citing the original paper, layer normalization was moved to the input of each subblock, similar to a pre-activation residual network, and an additional layer normalization was added after the final self-attention block. A modified initialization which accounts for the accumulation of the residual path with model depth is used. We scale the weights of residual layers, and the vocabulary has expanded to over 50,000 tokens. The authors also increased the context size from 512 to 1042 tokens, and they use a larger batch size of 512 examples is used. The vocabulary is not only expanded, but a modified idea of byte pair encoding called byte level byte pair encoding was also used in this model. The idea of byte level BPE is almost the same as the original BPE discussed in the previous lectures. However, here, instead of listing all single characters from our corpora, in Unicode there might be many of them, like over 1000. We start with a vocabulary consisting of single bytes, and then continue to produce merges. So instead of starting our vocabulary with hundreds or more single characters, we start with 256 values, and then merge them to produce longer pieces of information, syllabes, morphemes, or full words, like in the original BPE algorithm. What is probably most interesting and not mentioned yet The authors experimented with much larger networks, as the biggest version of GPT-2 model consists of 48 decoder layers, as compared to only 12 of them in the first version, and includes 1.5 billion parameters, as compared to 170 million parameters provided in GPT-1. So the biggest GPT-2 model is about 12 times bigger in terms of parameters than the previous iteration. And as we will see in a moment, this increase of size will have a key role in our story. OpenAI decided not only to experiment with the architecture itself, but they also decided to use a bigger dataset to train their language model. Instead of using books corpus, they used a subset of crawled websites. To prevent low-quality ones from being included in the dataset, they used a heuristics in which they crawled outgoing links from Reddit, but only those that had at least 3 karma assigned. As a result, they visited 45 million links and extracted their content. They collected websites not younger than December 2017 and post-processed them to clean up the data, for example, remove duplicates, and as a result, they obtained 40 gigabytes large corpus containing 8 million documents, and they called it web text. This dataset was used to pre-train a language model. Being equipped with larger networks and a much bigger dataset used to pre-train the language model, the next step was to evaluate the model without a supervised phase. Indeed, they didn't fine-tune the model on a specific dataset, nor train the classifier. They simply used the pre-trained model to perform zero-shot predictions. In other words, they wanted to verify how well the pre-trained language model can solve tasks without being explicitly trained to solve those tasks. If the results are good, it means that the language models have general knowledge stored in them. The authors verified the quality of the models on several tasks. Here we iterate over some of them. First, they evaluated GPT-2 on children books tests, or CBT for short. The goal of CBT is to examine the performance of language models on different categories of words, for instance, named entities, nouns, verbs, or prepositions. In terms of evaluation, we report accuracy on an automatically constructed clause test, where the task is to predict which of 10 possible choices for an omitted word is correct. Here, the language model can be directly applied. For each of the options, we can calculate the probability of that option, and then we can simply choose the most probable one. The use of GPT-2 led to great results. Even in a zero-shot scenario, the model generated state-of-the-art solutions, and comparing how well different sizes of models behave on that task, we see that the quality increases with bigger models, getting closer and closer to human level 1. Another related task is called Lambada. Here we also have to predict a given masked word, but the dataset is constructed in such a way that in order to do it, we need to process and understand at least the last 50 tokens before the gap. This task requires the model to model long-range dependencies between tokens. For this and other tasks, we will summarize the results in separate slides. Yet another interesting task, which is related, is the Winograd schema. The goal of this task is to measure the capability of a system to perform common sense reasoning by measuring its ability to resolve ambiguities in text. The task here is to choose a resolution with higher probability. As we can see in the example presented in the slide, we have sentences with 2 options included. Our goal is to detect which word fits better at a given position. And this can be done using raw language model. We simply check the probabilities of those sequences and choose the sequence that is more probable one. There are also some tasks that require not only to fill the gap with a single word or phrase, but to generate longer pieces of text. An example of such a task used in GPT-2's evaluation is COCA. which stands for conversational question answering. It provides documents paired with dialogues between a question asker and a question answerer about the document. COCA evaluates reading comprehension abilities and the ability to answer questions that depend on the conversation history. For example, a sample question here might be simply why, if we want to detect what are the motivations of given actions. And here the situation is quite interesting. We need to force the model to provide answers for our questions. But how can we do that using our provide the next tokens for a given text scenario? The answer is very clever. The authors decided to create a context, a prompt, in which we have a document for which we have a question, and then at the end of the context we add a capital A semicolon. This fragment, capital A semicolon, is frequently used in online resources. For instance, if we have questions and answers. We hope that the network, seeing that piece of text, will switch to answer the question mode and will continue with the answer. That's clever. Similarly, we use some tricks to solve the text summarization and machine translation tasks. Both of them are described in this slide. In the text summarization task, after a long form of a given document provided in the context, we add a special token, TLDR, representing too long didn't read, which is quite popular in the internet, and the model should be able to understand it. And then we let the model to produce at most 100 tokens. From the generated texts, the first 3 full sentences are extracted so that they represent the summaries. So here also, a special piece of text is used to encourage the model to follow a certain path, because after TLDR we expect a summary to be provided. Clever. But even more clever solution had to be applied in the context of machine translation. To force a model to process pairs of translated sentences, we built a context, a prompt first. The prompt contains several examples of pairs separated using the equal to sign. The authors focused on translation from English to French, so the authors provide several examples as the context first, and then added the English sentence finished with the equal to sign at the end of it. The model reads the context and tries to predict tokens that are the most likely continuation in that given context. And because it saw that after each equal to sign, a translation of the sentence before that sign was provided, it should follow that convention, because it is the most likely continuation. This is a mind-blowing scenario, but well, we will see how it works here and in subsequent iterations of GPT. Finally, they also evaluated the language models without using an external task, like summarization or question answering, and they used the intrinsic evaluation using a perplexity measure for this task. Perplexity tells us how perplexed the language model is by seeing a given sequence. And the idea is pretty simple. The language model itself can be used to assign probabilities to sequences of texts. A model trained on a given corpus should generalize well. Seeing a correct sentence from another corpora, it should assume that it is a likely sentence and assign a high probability, at least higher than some ungrammatical sentences or sentences which contain some fake content. So looking at a different text corpus, it should say this text is probable. However, the probability calculated will depend heavily on the length of the sequence. As we calculate the joint probability of the whole sequence, the longer the sequence, the lower the probability. To normalize it, we can introduce a normalization factor. Simply, let's calculate the root of the nth degree of the sequence probability. This way, we can compare values between sequences of different length. The perplexity is simply 1 divided by that normalized probability. As we can see, for correct, real-world sentences, a good language model should assign high probabilities so that perplexities should be close to 1. And they used this mechanism to check what is the perplexity measured on corpora other than web text, expecting it to be low. And the evaluation of that zero-shot scenario on various tasks led to interesting conclusions. As we can see, as the model grows, the number of parameters increases, the quality of answers also increases. The biggest evaluated model contains 1.5 billion parameters, and it seems that if we used a larger network, the trend should continue. For question answering, the accuracy is very low. However, the task we refer to here is the task in which we have to provide the answer, not select one from the predefined ones. Because the number of possible answers is enormous, those scores are not that bad. Moreover, the quality improves drastically with the size of the model. Finally, for example, for reading comprehension, we see that the zero-shot scenario outperforms some decent baselines, which are supervised solutions. The summary of scores comparing state-of-the-art scores with various sizes of the GPT-2 models is presented in this slide. The authors evaluated 4 versions of GPT-2 models. The smallest one relates to the original GPT model, introducing the same number of parameters. The second one relates to the BERT large model, containing a similar number of parameters, and as we can see, the most powerful model contains about 1.5 billion parameters. For some tasks, the authors provide both the evaluation metrics on a given task, an extrinsic evaluation score, and the perplexity measured on a given evaluation task, an intrinsic evaluation score. The difference between extrinsic and intrinsic evaluation lies in the context. In extrinsic evaluation, we determine the importance of the language model in the context of a given task. We ask what impact a given language model has on the quality of the solution. In intrinsic evaluation, we evaluate the language model itself using some metrics without the help of the external task. Here, the perplexity measured on Lambda is the intrinsic evaluation. The Lambda dataset is used just as a corpus of text, and GPT tells how likely it is to observe the text in that corpus. The perplexity calculated is over 10 times smaller than the existing state-of-the-art, so that a model trained on such a huge dataset can estimate probabilities of sequences much better than the existing approaches. Looking at the evaluation through the Lambda tasks lens, where we predicted the final token based on a long context, the quality of larger GPT-2 versions improved monotonically. 2 biggest models produce state-of-the-art solutions even without supervision. GPT also provides state-of-the-art perplexity on other corpora like PenTreeBank, PTP for short, Wikitext2 and Wikitext 103. As we can see, for various corpora, the model can estimate the probability of data best. The only dataset for which the perplexity is much worse is 1 billion words corpus. This is the biggest corpus with sentence-level shuffling, which removes all long-range structure, and this is the probably answer on why the perplexity is quite high here. In the context of extrinsic evaluation, the GPT models achieve state-of-the-art also on 2 kinds of CBT tasks: named entities prediction, or NE for short, and common nouns, or CN for short. For other tasks and scenarios, the results obtained were promising, so OpenAI decided to continue the research on those models. However, all those experiments show an interesting thing. Training a large language model that tries to predict the next token might be sufficient to solve a variety of tasks even without supervised fine-tuning. How is that possible? If we have a large corpus of text, various tasks will occur there. Even if you think about tasks such as machine translation, as we can see in this slide, we can find examples of sentences translated to other languages in the text. So if we have a huge dataset and train a huge model, there is a chance that the quality will increase because the model will notice examples of such tasks. And the solution that was used in the context of machine translation for GPT-2, which involved giving a small set of examples as the contexts, might be really useful. And this way we reach the next milestone, GPT-3. GPT version 3. This model was introduced in 2020 in a paper entitled Language Models Are Few-Shot Learners. The main goal here was to investigate the few-shot learning abilities of GPT models, like in the context of a machine translation task we just mentioned. And well, they increased the model size quite a lot. The original GPT contained 170 million parameters. GPT-2, the large version of GPT-2, contained 1.5 billion parameters. And the biggest GPT-3 model contains 175 billion parameters. It's about 1,500 times bigger than the original GPT, and it was released just 2 years after the original GPT-1. As I stated just a second ago, GPT version 3 is huge. In that scenario, a classical approach in which we fine-tune a model by updating the weights based on some examples iteratively is way too costly. Just imagine calculating gradients for all the weights in thousands of iterations. For this reason, the authors focused on the analysis on how models can be guided without the adaptation of the parameters of the network. They evaluated 3 scenarios. Zero-shot learning, which we covered in previous slides, where the model predicts the answer given only a natural language description of that task without gradient updates. We simply predict the next tokens based on a given context. Here, in this example, given the prompt translate English to French, new line cheese arrow, we expect the next token to be the translation of the word cheese. Subsequently, they analyzed a one-shot scenario, in which besides the task description, the model sees exactly one example of the solution. Also, here, no gradient updates are applied. As we can see in this prompt, we give the model one example of a translation for sea otter here, and expect the model to follow that convention, which is the most likely continuation. Finally, the few-shot scenario focuses on giving the model several examples. In this way, we emphasize the convention even more, so that given the prompt on this slide, we humans can be sure that the continuation of this text should be the translation, so that we hope that the network does the same. The idea of few-shot learning relates to the concept of in-context learning. In-context learning is the emergent ability seen in the large language models, where based on input-output examples, without calculating the gradient, we try to solve a task. Assuming that we have a large enough dataset, there will be many sequences where we have examples of tasks provided. For example, having a frequently asked questions sections on websites, we may have lists of questions and answers. Each question will be prefixed with Q or question and a semicolon, and each answer will be prefixed with A or answer with semicolon. Similarly, some equations might involve examples on how to add numbers, etc. Maybe the models can learn from these examples, and maybe if we create appropriate prompts, maybe they can follow those conventions. The in-context learning may focus on nuances in the contexts. Looking at this image coming from the website, a blog from AI Stanford, analyzing the topic of in-context learning in depth, I strongly encourage you to visit that blog. We see 2 very similar prompts two very similar contexts, providing some information about the examples. Both columns present the same inputs, but the desired outputs provided after the double slash sign are different. The left column expects the model to provide the information about the sentiment related to that text, and the right column focuses on assigning a topic like finance, sport, or tech. Then the last input is provided along with the double slash separator, and the network, based on the previous context, on the prompt provided, should provide the most likely continuation, which in the left-hand side context might be a word positive, and in the right-hand side context we might expect the word finance to be produced. This behavior is achieved by only presenting several examples which set the language model to a given mode. And even we, humans, know easily what the convention is in both of the cases. And we achieved it without modifying the network. We simply extract the answer using forward propagation here. Before we analyze what evaluation scores can be achieved using this approach, let's discuss the details on the architecture of the GPT-3 model. In fact, OpenAI provided several model sizes, and when they refer to the GPT-3 model, they refer to the biggest one, containing 175 billion parameters. What is worth noticing here is that there is an enormous batch size equal to 3.2 million used. There are 96 attention heads, and the dimensionality of each head is set to 128. So this leads to a huge embedding size of over 12,000 elements produced by each of 96 layers. What is also very important and not mentioned in this table, the GPT-3 model can handle even longer contexts than the previous iterations. It can consume the last 2048 tokens. Such a huge network needs an appropriate amount of data to be trained on. The authors of GPT-3 used the common crawl dataset, which consists of a dump of crawled websites. The dataset was filtered to remove low-quality data and post-processed using the duplication procedure to remove duplicates. To increase the diversity of the dataset was enriched with other non-high-quality reference corpora. The result? About 570 gigabytes of data, over 14 times more than the dataset used to train the GPT-2 model. The GPT-3 model variants were evaluated on various tasks, comparing zero-shot, one-shot and few-shot scenarios to existing approaches. The first one was the lambda task, which we already discussed in the context of GPT-2. Here our goal was to predict the next token based on a long context we need to understand to choose the appropriate token, appropriate continuation. The previous state-of-the-art was achieved by GPT-2, and now we see that the new GPT models beat the state-of-the-art by a large margin. On the x-axis we see the model size, and the bigger model achieve better accuracy. Moreover, the best combination is to use the biggest GPT-3 model in a few-shot scenario, providing k equal to 15 examples in each prompt. As GPT-3 can handle fairly long contexts equal to 2048 tokens, we can fit so many examples in that context. What is interesting here, giving only one example seems to decrease the quality as compared to the zero-shot scenario. In a few-shot case, the prompt is formed in the following format. We provide a list of examples with the context followed by a blank space and an expected answer after an arrow. Then we put the example for which we want to obtain the answer and finish the prompt with the arrow so that the GPT model should provide the most likely continuation, which is expected to be the answer. Some mind-blowing results are obtained on Trivia QA dataset containing questions for which we need to generate answers. The questions sometimes might be quite hard to answer, like for example, what hero from Greek mythology was killed by a discus thrown by Apollo, who then named a flower after him, made from his spilled blood? Or Caroline on Brunswick was the queen consort of which British king? Similarly to the previous slide, the biggest model scored the best, beating even a fine-tuned state-of-the-art solution. This best case is the full GPT-3 model with 64 examples of questions and answers provided in the prompt. The accuracy of the model is equal to 71.2, which is higher than the previous state-of-the-art solution by about 3 percentage points. The next evaluation shows how good GPT-3 is in the context of neural machine translation tasks. As we can see here, the few-shot scenario scores best from the 0, 1 and few-shot options. And for some cases, GPT-3 even beat supervised state-of-the-art solutions. Here we can see that GPT-3 produced slightly better results on French to English translation and German to English, but in that context the difference is quite small. Another interesting evaluation was made on the PICA dataset, which focuses on physical common sense knowledge. Physical QA is a binary choice task, often better viewed as a set of two goal and solution pairs. For example, we have to decide what is more probable choice to achieve the following goal. To separate egg whites from the yolk using a water bottle, you should, solution 1, squeeze the water bottle and press it against the yolk, release, which creates suction and lifts the yolk. Or solution 2, place the water bottle and press it against the yolk, keep pushing, which creates suction and lifts the yolk. All zero-shot, one-shot and few-shot models containing 175 billion parameters achieve scores better than the previous state-of-the-art, with the best answers provided by a few-shot scenario, with k equal to 50 examples provided in context. This shows that the model can model common sense knowledge also. The next slide provides an analysis of another question answering task, COCA, which we introduced in the context of GPT-2. These scores are interesting because we have a reference human score provided. As we can see here, for a task where we have to answer questions related to conversations, the biggest model in a few-shot setting with k equal to 5 examples achieves near human level performance. Additionally, I found an analysis of the abilities of the language model to solve mathematical tasks really interesting. As we can see here, the largest models start to learn the idea of adding and subtracting digits. The highest scores are achieved evaluating on the addition and subtraction of numbers consisting of 2 digits. And this might be expected, as the number of 2 digits numbers is much smaller than 3 digits and 4-digit numbers, and there is a high chance that many of those examples were seen during the training phase. And these charts show the impressive abilities of large pre-trained language models used in a few-shot scenario. The quality of the texts produced by the model is so high that even humans have huge problems determining whether a given piece of text was written by a human or not. The mean accuracy measured on people making such a decision is only a little above the random choice. The GPT-3 model was the first model that was not open sourced. According to Wikipedia, Microsoft announced on September 22, 2020 that it had licensed exclusive use of GPT-3. Others can still use the public API to receive output, but only Microsoft has access to GPT-3's underlying model. The huge successes of large pre-trained language models are undeniable. However, as the model size increases, the size of the dataset used also increases. This led to the decision to move from the curated sets, such as books corpus, to dumps of websites from Common Crawl, which are noisy and represent opinions of virtually the whole humankind. These might include biased, harmful, toxic, or documents containing fake data, as this is the internet we have. By the way, there is a great video on YouTube made by Yannick Kilcher who trained a GPT model on 4chan, which, as the title of the video says, is the worst AI ever. I strongly recommend watching this video as the whole experiment was great. The bigger the datasets become, the harder it is to assure the quality of the data. And without this, it's hard to prevent a given model from producing wrong outputs. Imagine a company producing electronic devices, which integrates a large language model into their software. And some user asks the model to provide the best producer out there. What if, based on the dataset the model was trained on, the model outputs a sequence in which it suggests buying devices produced by other producers and suggests to sell the device that hosts the model? Well, that would be quite unfortunate, at least. We see that predicting the next token on a web page from the internet is a little bit different than the objective of following the user's instructions helpfully and safely, which causes some problems. It would be perfect if we could create models that align better with our human preferences. It would be better if we could predict the best answer from a human perspective, not only from the perspective of the dataset we trained on. And this is something that is proposed in the InstructGPT model, which follows the same approach as a very popular model called ChatGPT. The idea behind those two models are the same, and probably what differs them is the dataset used. But the training procedure is shared. The paper entitled Training Language Models to Follow Instructions with Human Feedback was published in March 2022 by, well, OpenAI. This paper is published on arXiv and the link to it is presented at the bottom right corner. This model is a clever integration of reinforcement learning with GPT language models, utilizing the idea of RLHF, which stands for Reinforcement Learning from Human Feedback. By applying such an approach, they produced a series of models called InstructGPT, which were trained to follow instructions. Even the smallest model, despite being over 100 times smaller than GPT-3, the smallest one has 1.3 billion parameters as compared to 175 billion parameters in full GPT-3, but we also had bigger InstructGPTs which contained 6 billion and 175 billion parameters. And the outputs generated by the smallest model were preferred by humans even than the outputs of the large GPT-3 model. So, using only 1.3 billion parameters, we had a model which behaves better than the large 175 billion parameters big GPT-3. The authors showed that, citing the original paper, InstructGPT models show improvements in truthfulness and reductions in toxic output generation while having minimal performance regressions on public NLP datasets. The goal of training a language model to act in accordance with users' intentions might be achieved if human feedback is taken into consideration. The process is visualized in detail in this slide. The first step is to gather a dataset of prompts containing inputs for which the answers should be provided. This included, for example, questions, explanation requests, opinion requests, and others. Here we can see an example prompt asking to explain the moon landing to a 6-year-old child. In total, 13,000 prompts were collected. These prompts were answered manually by humans, which were carefully selected by OpenAI to ensure good data quality. They wrote the best answer they could. Then, the GPT-3 model was fine-tuned. Hello, supervised learning, long time no see. On those best answers provided by humans. This step is used to make the model able to follow humans' expectations more carefully. However, the next steps are crucial. In the second step, the model provides a list of candidates for a given prompt, So we can see that in the context of our example prompt, explain the moon landing to a 6 years old, we have 4 candidates for answers. And the first one starts with the description of the gravity, which is related but probably shouldn't be included in the story for a 6 years old kid. And the B answer describes war, which is totally unrelated, and we don't expect that stuff for children. C option looks better but covers details that might be hard to be understood by children. And finally, D seems to be the best one. In this step, the annotators were asked to compare the answers. They answer questions such as, in my opinion, is answer D better than A? And as a result, a ranking of preferences is constructed. This is a very important signal as it tells what humans prefer, and integrating it into the training process as an objective could help a lot to produce better answers. However, human annotations are costly, so that they use the preference annotations to train so-called reward model, which tries to assign preference scores to answers, like humans do. Better answers obtain better scores. So this model tries to mimic the annotator. The reward model might be constructed based on the language model. We simply remove the last layer, the classification layer, which chooses the next token in a sequence, and use the stored knowledge to fine-tune a reward model. The authors provided several sizes of language models. However, they used the middle language model, the one with 6 billion parameters, to train the reward model, because training the full 175 billion parameters model was too unstable in the context of the reward model. In each training step, the model sees pairs of answers for a given prompt and tries to assign rewards. The difference between those scores is then a single number, because each reward is a number, and the difference between them is also a number, so that the difference is passed through the sigmoid function and the logarithm. Then, for a set of k possible responses, we iterated over them to form a full loss function. If the first answer is preferred, it obtains a higher score so that the difference will be greater than 0 and the sigmoid output will be likely close to 1. Otherwise, the difference will be smaller than 0 and the sigmoid of it will be close to 0. And yeah, this is the cost function. This is the cost function that was used to train the reward model. So if we have a model that can assign rewards to a given answers, we can integrate it into the final step that uses reinforcement learning. Having a model which can substitute a human being in the answer quality rating process, we can train another model which will produce best answers. At this step, having a given prompt, we optimize a policy against a reward model using the reinforcement learning. Here, a given prompt is processed using the policy so that the policy produces the candidate answer. Our reward model we have trained in the previous step is used to rate this answer, and the rating, the reward calculated, is used to update the policy. The model learns to maximize the reward. It learns how to produce answers which will obtain the highest rewards, which will be preferred by those models. And because those models, those reward models were trained on human preferences, the goal is to mimic, is to follow those human preferences. And voila! The side effect of it is a model which follows instructions much better. While we don't know all the implementation details on ChatGPT, we know that these models, InstructGPT and ChatGPT, are siblings, as the OpenAI itself stated in one of the blog posts linked in this slide. They probably differ in datasets, but the general idea of utilizing the human feedback as presented in the previous slide was used both in InstructGPT and ChatGPT models. The results obtained showed that users prefer answers provided by InstructGPT. Citing the original paper, we find that GPT-3 outputs performed the worst, And one can obtain significant step size improvements by using a well-crafted few-shot prompt, GPT-3 prompted, then by training on demonstrations using supervised learning, which is referred to here as SFT, which stands for supervised fine-tuning. And finally, by training on comparison data using PPO, which refers to proximal policy optimization, the reinforcement learning related model, which we described in the step 3 of that process. They also noticed that InstructGPT outputs are more appropriate in the context of a customer assistant, more often follow explicit constraints defined in the instruction, for instance, write your answer in 2 paragraphs or less, and are less likely to fail to follow the correct instruction entirely and make up facts, hallucinate. Hallucinations here are defined as facts that are made up. For instance, if we ask the model to answer the question who is the president of Poland, and if it answers Bill Gates, this is not true. This is a hallucination of the model. And we see that the InstructGPT model hallucinates less often in closed domain tasks. These results suggest that InstructGPT models are more reliable and easier to control than GPT-3. However, it is also interesting to see some comparison of the outputs generated by GPT-3 and InstructGPT to understand why in some cases InstructGPT is better or why we think that it gave us an inappropriate answer. In the first example, we have a piece of code with the following question: what is the purpose of this code? The GPT-3 model thinks that the most likely continuation is the list of options to choose from. While it might be a reasonable interpretation, this is probably not something that the user wanted to achieve. So this is a misalignment of the goal and the action performed. The InstructGPT model provides a much better answer explaining that piece of code. On the right-hand side, we see another example where both models fail. GPT-3 makes up facts, it hallucinates, while InstructGPT provides an answer which is way too general. Instead of this long story, it should simply answer the pumpkin will explode. And that should be all. The InstructGPT model was trained in 3 sizes, with the language model consisting of 1.3 billion parameters, 6 billion parameters, and 175 billion parameters. The reward model, however, in each case was trained using 6 billion parameters. We don't know the details on ChatGPT model yet, but we know that the same approach was utilized here. The idea of constraining the responses of the language models using InstructGPT was applied in parallel to the continuation of the research on regular GPTs. Shortly after ChatGPT was released, a new, let's say, classical GPT model, GPT version 4, was released. We don't know much about it yet. We know that it's better and bigger and only several more things. The lack of details led to creation of some funny memes like this one on this slide. However, we know that GPT-4 is not unimodal. It is trained on 2 modalities, texts and images. And this is a huge step forward, as relating words to images might be crucial to understand the world better. Moreover, we also know that the context window is much larger. There are various versions of GPT-4. The smallest one has the context window of 8,192 tokens. It's 4 times bigger than the context handled by GPT-3, and the largest one can handle over 32,000 tokens, so 16 times more than GPT-3. This might make us believe that GPT-4 is much bigger than GPT-3. All this story shows an amazing achievement of humankind. Now we have great tools that might solve many NLP problems that require understanding human language. However, we have some new problems that need to be solved. In our today's lecture, we learned that bigger models have better abilities. However, the sizes of recent models, such as GPT-3, are so big that it is impossible for us to run a model on our machines. The 175 billion parameter GPT-3 model, assuming that each parameter needs 32 bits of memory space, requires 652 gigabytes of RAM just to load the model. This is way too big to be loaded on personal computers. Moreover, even companies have problems loading it, not to mention fine-tuning it. This relates to another problem. Large language models need to be trained. The total cost of 175 billion parameter GPT training is estimated to be around $4.6 million. And this assumes a single training process. Frequently, however, we have some bugs in code, data quality issues we need to optimize hyperparameters. The real costs might be much bigger. Moreover, trying to train such a model is not only costly, but also takes a lot of time. If we used a single NVIDIA V100 GPU, a powerful one, it would take about 355 years to train the GPT-3 model. To train these models, we need large clusters of GPUs that can parallelize the work. This is a big challenge in the context of research. The preparation of new language models became so expensive that smaller companies and universities might have problems to compete. We need to find ways to create smaller models or to provide training procedures that can optimize only a subset of those parameters, because the cost of training those language models is too big. We also see that the model size increases and the abilities of those models also increase. Recent models like GPT-4 can handle very long contexts, but these need to be optimized on a large enough dataset. Having gigabytes or terabytes of data, assuring appropriate data quality becomes a huge challenge. How to understand what each of the thousands of attention heads do? How to prevent models from producing harmful answers? The second question was partially addressed by utilizing human feedback in the context of InstructGPT. However, still, the internet is messy and we always have to keep in mind that the results produced by language models will be unpredictable, especially if we don't know what the data represent. However, modern language models give us huge possibilities. We all heard and probably used ChatGPT, which can help us find answers to our questions. Those models revolutionize the way we search for information in the internet. Instead of searching for websites providing answers to our questions, we can simply generate those answers. We can generate copilots, which help us write and debug code, and it seems that ChatGPT and GPT-3 and 4 will have a huge influence on our daily lives. However, we still need to find answers on how to train the models more effectively, how to control the quality of the models, and how to make those models smaller so that they can be hosted on our computers. Thank you very much and see you later.